Applied optimization problems. Hello everyone. Today, we are beginning our study of applied optimization problems. To start, let's look at what optimization actually means. In a general sense, optimization is the process of finding the best possible solution to a problem from a variety of available alternatives. Now, when we translate this concept into the language of mathematics, the idea of the best solution typically refers to finding either the maximum or the minimum value of a specific quantity. For instance, in a real-world scenario, this could mean maximizing the area of a plot of land or minimizing the cost of production. As grade 12 calculus students, we use derivatives as our primary tool to find these optimal values. By calculating the derivative, we can identify critical points, which are the candidates for our maximums and minimums. Once we find these points, we then test them to confirm which one provides the optimal result. Over the next few slides, I will guide you through the systematic strategy we use to translate these verbal problems into mathematical models and solve them. The general strategy for solving optimization problems. Now that we have established what optimization is and why we use derivatives to find these values, let's move on to the actual process. Solving a real-world optimization problem requires a systematic approach to translate a verbal description, essentially a word problem, into a mathematical model that we can actually solve. To do this, we follow a series of structured steps. First, you must identify the objective. This means determining exactly what needs to be maximized, such as area, volume, or profit, or minimized, such as cost, distance, or surface area. You cannot start the math until you know exactly what the best solution looks like for that specific problem. Second, we assign variables. We need to give mathematical symbols to the unknown quantities. For example, we might let x represent the length and y represent the width of a rectangle. Third, we establish the constraint. In most real-world scenarios, you are limited by certain conditions. This is the constraint. For instance, if a problem states that the total length of a wire is 100 meters, that is a fixed value that limits your options. Fourth, we formulate the objective function. This is where you write the equation for the quantity you want to optimize. A very important point here is that if your function contains more than one variable, you must use your constraint equation to substitute one variable for another, expressing the entire function in terms of a single variable. Fifth, we find the critical points. This is where the calculus comes in. You calculate the first derivative of your function and set it to 0, which we write as f prime of x equals 0, to find the points where the slope is 0. Sixth, you must verify the nature of the point. Simply finding a critical point is not enough. You have to prove whether that point is a maximum or a minimum. To do this, you will use either the first derivative test or the second derivative test. Finally, we solve for the final answer. Once you have the optimal value for your variable, you substitute it back into your original equations to find the required dimensions or the final maximum or minimum value. In the following slides, we will apply this exact step-by-step strategy to two different examples to see how it works in practice. Example 1. Maximizing the area of a rectangular plot. Now that we have established the general strategy for solving optimization problems, let us apply those steps to a practical example. Please look at the problem on the slide. A farmer has 40 meters of fencing material and wants to enclose a rectangular garden. Our goal here is to determine the specific dimensions that will allow the farmer to maximize the total area of the garden. Following the systematic approach we just discussed, we begin with step 1, identifying our variables and constraints. First, we need to assign symbols to the unknown quantities. Let the letter L represent the length of the garden and the letter W represent the width. Next, we must identify the constraint. In this scenario, the constraint is the total amount of fencing available, which is 40 meters. Since the fence goes around the outside of the rectangular garden, this 40 meters represents the perimeter. The formula for the perimeter of a rectangle is 2 times the sum of the length and the width. Therefore, we can write our constraint equation as 2 times the quantity length plus width equals 40. To simplify this equation for later use, we can divide both sides by 2, which gives us length plus width equals 20. By rearranging this, we can express the width in terms of the length, resulting in the equation. Width equals 20 minus length. This is a crucial step, as it allows us to reduce our problem to a single variable, which we will use in the next slide to formulate our objective function. Example 1 continued, maximizing the area. Now that we have established our constraint from the previous slide, let us move on to step 2, which is formulating the objective function. In this specific problem, the quantity we are looking to maximize is the area, which we will represent as capital A. We know that the area of a rectangle is calculated by multiplying the length, L, by the width, W. However, to perform calculus, we need our function to be in terms of a single variable. Therefore, we will substitute the constraint we found earlier, where width equals 20 minus length, into our area formula. This gives us the area as a function of length, of L equals L times the quantity 20 minus L. When we distribute the L, the expression becomes 20L minus L squared. With our objective function now simplified to one variable, we proceed to step 3, finding the critical point. To do this, we must find the first derivative of the area function with respect to length. Differentiating 20L minus L squared gives us 20 minus 2L. To find the critical point, we set this derivative equal to 0. So, 20 minus 2L equals 0. By rearranging the equation, we get 2L equals 20, which, upon dividing by 2, tells us that the length, L, equals 10. Now that we have found a potential optimal value for the length, we will move to the next slide to verify whether this point actually represents a maximum area. Example 1 continued, maximizing the area. Now that we have identified the critical point where the length is 10, we must not simply assume this is our maximum. As we discussed in our general strategy, we need to verify the nature of this point. Moving to step 4, we will use the second derivative test. To do this, we find the second derivative of the area function with respect to length. By taking the derivative of our previous result, which was 20 minus 2L, we find that the second derivative of A with respect to L is equal to minus 2. Because the second derivative at our critical point of 10 is minus 2, and since minus 2 is less than 0, the second derivative test confirms that the function reaches a local maximum when the length is 10. Now that we have verified the maximum, we proceed to step 5 to determine the final dimensions of the garden. If the length is 10 meters, we can refer back to our constraint equation from the previous slide, where width equals 20 minus length. Substituting 10 for the length, we get 20 minus 10, which means the width is also 10 meters. Consequently, the garden should be a square with dimensions 10 meters by 10 meters to achieve the maximum area, which calculates to 100 square meters. Having completed this example on rectangular areas, we will now apply these same systematic steps to a more complex three-dimensional problem involving a cylinder in the next section. Example 2, minimizing the surface area of a cylinder. Now that we have seen how to maximize the area of a rectangle, let's move on to example 2, where we will apply the same general strategy to a three-dimensional object. In this problem, we are designing a cylindrical can that must hold a fixed volume, which we will represent by the letter V. Our goal is to find the specific ratio of the height, h, to the radius, r, that minimizes the amount of material used. In practical terms, minimizing the material means we need to minimize the total surface area of the cylinder. Following the systematic approach we discussed in the earlier slides, our first step is to identify the objective and the constraint. First, let's look at the objective. We want to minimize the surface area, which we will call S. The formula for the total surface area of a cylinder, which includes the top and bottom circles as well as the curved side, is S equals 2 pi r squared plus 2 pi rh. Next, we identify the constraint. The problem tells us that the volume is fixed, meaning V is a constant value. The formula for the volume of a cylinder is V equals pi r squared h, just as we did in the previous example with the garden. This constraint is essential because it provides the relationship between our two variables, r and h, which will allow us to rewrite our objective function in terms of a single variable in the next step. Example 2, continued, minimizing the surface area. Now, let us proceed to step 2, where we express the objective function in terms of a single variable. As we noted in our general strategy earlier, we cannot easily differentiate a function that depends on two different variables, so we must use our constraint to simplify the equation. Starting with the volume formula we identified on the previous slide, we can isolate the height, h, by rearranging the formula. We find that h equals v divided by pi r squared. Next, we substitute this expression for h into our surface area formula. This allows us to write the surface area, S, as a function of the radius, r. The equation becomes S of r equals 2 pi r squared plus 2 pi r times the quantity v over pi r squared. When we simplify this by canceling out the pi and one of the r terms, we arrive at the simplified objective function. S equals 2 pi r squared plus 2v over r. Now that we have a function of a single variable, we can move to step 3, which is finding the critical point. To do this, we calculate the first derivative of s with respect to r. The derivative of 2 pi r squared is 4 pi r, and the derivative of 2v over r is negative 2v over r squared. Therefore, s prime of r equals 4 pi r minus 2v over r squared. To locate the critical point, we set the first derivative equal to 0. This gives us the equation, 4 pi r minus 2v over r squared equals 0. By moving the second term to the right side, we get 4 pi r equals 2v over r squared. If we multiply both sides by r squared to clear the fraction, we obtain 4 pi r cubed equals 2v. Finally, by dividing both sides by 4 pi, we find that r cubed equals v divided by 2 pi. In the next slide, we will verify whether this critical point represents a minimum value using the second derivative test. Example 2, continued, minimizing the surface area. Now that we have identified the critical point in the previous slide, we must ensure that this value actually represents a minimum surface area and not a maximum. To do this, we proceed to step 4, verifying our result using the second derivative test. If we take the second derivative of s with respect to r, we get 4 pi plus 4v divided by r cubed. Now, consider the physical context of our problem. Both the radius, r, and the volume, v, must be positive values. Because all terms in the expression are positive, the second derivative of s with respect to r is guaranteed to be greater than 0. As we discussed in our general strategy, a positive second derivative confirms that our critical point is indeed a local minimum. With the verification complete, we move to step 5 to find the specific ratio of height to radius. We start by taking our critical point equation, which was 2v equals 4 pi r cubed, and substitute the formula for volume, pi r squared h. In place of v, this gives us the equation, 2 times pi r squared h equals 4 pi r cubed. To simplify this and find the ratio, we divide both sides of the equation by 2 pi r squared. This leaves us with h equals 2r. By dividing both sides by r, we find that the ratio of h over r equals 2. In plain English, this tells us that to use the minimum amount of material for a fixed volume, the height of the cylinder should be exactly twice the radius. Since twice the radius is the diameter, the most efficient design is a can where the height is equal to its diameter. Now that we have mastered these two examples, let's move on to the next slide, where we will discuss some common mistakes to avoid so you can ensure full marks on your exams. Common mistakes to avoid. Now that we have walked through the practical examples of the rectangular garden and the cylindrical can, let us discuss some common pitfalls to ensure you avoid them in your exams. First, be careful about ignoring the constraint. A frequent mistake students make is attempting to differentiate a function that still contains two variables, such as length and width. As we saw in our previous examples, you cannot find a simple derivative if the function depends on two independent variables. You must first use the constraint equation to express the objective function in terms of a single variable before you begin the differentiation process. Secondly, do not forget to verify your results. Simply finding a critical point where f prime of x equals 0 is not sufficient. You must apply either the first derivative test or the second derivative test to formally prove whether that specific point is a maximum or a minimum. Without this verification, you haven't technically proven that the solution is the optimal one. Thirdly, be mindful of your units. Because these are applied, real-world problems, a number by itself is incomplete. Always ensure that your final answer includes the appropriate units, such as square centimeters for area, meters for length, or kilograms for mass. Finally, avoid boundary neglect. In certain problems, your variable may be restricted to a closed interval, ranging from a value a to a value b. In such cases, the absolute maximum or minimum might not occur at a critical point where the derivative is 0, but could instead be located at the endpoints of the interval. Therefore, always check the function's values at these boundaries to ensure you have found the true optimal solution. Key takeaways. To wrap up our lesson on applied optimization, let's review the key takeaways to ensure you have a solid grasp of the process. First, remember that optimization is essentially the practical application of derivatives to find the most efficient or best value of a function, whether that means the highest possible profit or the lowest possible cost. Next, we have the objective function. This is the mathematical equation representing the specific quantity you are trying to maximize or minimize. Think back to our examples. The area of the rectangular garden and the surface area of the cylindrical were our objective functions. Then we have the constraint. This is the fixed condition or limitation provided in the problem. As we saw in our exercises, the constraint is crucial because it allows us to express the objective function in terms of a single variable, which is a necessary step before we can differentiate. We also focused on critical points. These are the values where the first derivative of the function equals 0 or where the first derivative is undefined. These points are our primary candidates for the optimal values we are searching for. Finally, always remember that verification is essential for a complete solution. Simply finding a critical point isn't enough. You must use a tool like the second derivative test. Remember, if the second derivative of the function is less than 0, you have found a maximum, and if the second derivative is greater than 0, you have found a minimum.